Find the center of mass for the region x squared plus y squared less than or equal to x. And for some mysterious reason, it also gives it to you in polar coordinates. This often happens if the region has a nice description. And if you look at what the region is, x squared plus y squared equals x, it's a circle. And like, circles are nice. Now, it's not centered at the origin, so the circle isn't, r equals something, but it's not too bad. The curve is r equals cosine theta. So this is r equals cosine theta, going from negative pi halves to positive pi halves. And we're given that the density looks very polar-like, square root of x squared plus y squared, or just r. And the question, center of mass. And we have some references here. So in case we have to integrate a high power cosine, we don't have to do it from scratch. So we have 5 answers, or at least 5 potential answers. Do we know what it is? Has somebody worked it out? Let's make a comment about something we can probably be saying is both very tempting and then say, this can't be the right answer.
C.
C is very tempting?
Yes.
Okay, C is very tempting. Somebody said, aha! Why is C very tempting? You say, well, hey, there's a half. Right in the middle. Right in the center. Shouldn't that be the center of mass? 1/2, 0, very tempting. Very tempting. Why is it not 1/2, 0?
The circle is not based in the center or at the origin.
Well, okay, the circle is not centered at the origin. True, but that's not the issue per se. What's the problem?
Can't the center of mass be anywhere along that line when you have no exact?
Well, it could be anywhere along this line, but why do we know it's not a half? In fact, not only do we know it's not a half, we know which side of a half it should be on. Ah.
Since it's not centered at the origin, the weight is biased towards the right side.
Now I feel like I'm going to give you a physicist response. I think you meant to say mass instead of weight. They're slightly different. But right idea. There's more mass the further out you are from the origin. So it's very sparse near the origin, but very dense over on the left-hand side. So sparse on the left, dense on the right, because the right has a higher density. If that's the case, which side of a half should you be on? You should be on that side of a half. So a half, though it's very tempting to look at, because it feels like, hey, shouldn't the center of mass be the center? Not necessarily. It depends on density. If density had been uniform, life is good. It was not uniform. All right, so that means we've got to do work. So what do we need to do? Well, spoiler alert, I can tell you the y-coordinate is 0 because all the options have 0. Even if all the options didn't have 0, why is the y-coordinate for the center of mass 0?
Because we have this, even if the density is different the farther left you go, it is still on the x-axis.
Yeah, so even though the density gets denser on the right versus the left, when we compare flipping across the axis, it won't change it. So if you look at a little piece up here versus a little piece down here, they'll have the same amount of density because they'll have the same distance from the origin. Okay, so by symmetry, y bar equals 0. Unfortunately, that's not enough for us to get the right answer. But if this was a long answer, that was just 2 points by writing that down. All right. So how do you find x bar? What do you need to compute? I'll give you a moment to think about this. But just one moment. Not 2 moments, just 1 moment. So if we want to compute x bar, what do we need to compute? We need to compute 2 things. Mass and moment with respect to y. Yeah, it's that weird thing, right? It's that weird notation. All right, which one do you want to tackle first? We're doing mass. All right. We're just doing that one first. How do you find mass? What's the basic idea? Mass is the integral of density. All right, well, we're going to go straight to polar. We're not going to pass go. We're not going to collect $200. What's our density? R. What is dA? R dr d theta. So the r squared comes from the density plus the little bit of dA. Where does theta go between? Negative pi over 2 to pi over 2. Because it told us, that's very nice that they did that. Where does r go between? 0 to cosine theta. So, well, you integrate r squared, and what do you get? Integral of r squared?
R cubed over 3.
Yep, r cubed over 3. Evaluate r equals 0 to r equals cosine theta. So we can pull out a 1/3. When you plug in 0, you get 0. When you plug in cosine theta, you get cosine theta. So that's negative pi halves to pi halves of cosine cubed theta. Well, do we know what the integral from negative pi halves to pi halves of cosine cubed theta d theta is? They gave it to us. So this is 1/3 times 4/3, 4 over 9. All right, that's the mass. Halfway. So now we'll do our moment. So we begin. What's the difference between mass and moment? What do you add in? A distance. Yes. It's a distance density dA. The major part is the dA. All right, so integral. Distance, when we do a moment with respect to y, what are we measuring? X. Now, we're in polar, so we don't write x. What do we write?
R cosine theta.
R cosine theta, because in polar, x equals r cosine theta. Density still r. dA is still r dr d theta. So if you multiply r cosine theta times r, you get r cubed cosine theta. And you have a dr d theta. The bounds are the same. So negative pi halves to positive pi halves for theta, 0 to cosine theta for r. And we say, okay, we integrate. What's the integral of r cubed with respect to r?
R to the 4th over 4.
Yeah, r to the 4th over 4. So negative pi halves to positive pi halves, 1/4 r to the 4th cosine theta. Evaluate that from r equals 0 to r equals cosine theta d theta. Well, the 1/4 we can pull out. When you plug in 0, you get 0. When you plug in cosine theta for r, you get cosine to the 4th theta, but there's another cosine theta. So that gives us the integral from negative pi halves to positive pi halves of cosine to the 5th. Do we know what the integral of cosine to the 5th theta is? Yeah, they gave it to us. And they're probably thinking, wait, why did they give us extra stuff? In case you made mistakes. They're there as distractors. So we know people make mistakes. We anticipate. It's one of the things we do is we say, what are some common mistakes? We'll throw those in. So you have to be careful. Just because you see the answer that you're getting doesn't mean it's the right answer. So check yourself. All right, 1/4 times 16 over 15, also known as 4 over 15. So that goes upstairs. At this point, what can we knock out? Yeah, there's no pi's in there, our answer. So, we can knock those out. But we can do more than just knock stuff out. If you want to divide by fractions, you just take the bottom fraction, bring it upstairs, but turn it upside down. The 4's cancel. 9 over 15. Unfortunately, it's not one of our options, but we haven't simplified. What's another way to write 9 over 15? 3 over 5. So the x-coordinate should be 3/5. And there we go. I'm pretty sure this was from an old exam. Good times, good times. And then we did give you this on the old exam. Because the point of this course is not to test you on your integration per se. Yes, we will test you on really basic integration. It's on, can you set things up and faithfully carry them out? And that's hard enough. That's hard enough. All right. Any questions?
Like r to the power of 3 that came from the my.
This one? There's 3 r's. There's an r coming from distance, an r coming from density, and an r coming from the dA. So that's where all the r's come from. So this is why you have to be careful. It's easy to miss an r. Now we didn't quite finish up last time. We threw this up and we said, hey, there's one other thing. We talked about moments. But as the hobbits would say, we've had one moment, yes, but what about second moment? And that has a name in physics. It's called inertia. Now, why is inertia the same thing as the second moment? You should ask a physics teacher. But for us, we'll just say we'll go with it. And the only difference we mentioned at the end of class was the distance term. The reason we call it the second moment is because you square the distance. So the first moment is like to the power 1. Is there a 0th moment? There is, but it has another name. What have we been calling the 0th moment? If you raise this to the power 0, what do you get? 1. So what you end up with, integral of density, which is mass. So mass, moment, inertia, they're all connected. You might say, are there higher moments? Yes. Will we talk about them? No. But the key to remember is, it's very similar, just remember distance squared. Other than that, proceed as before. You'll know it's inertia because it'll probably say the word inertia. Or if you see an I for inertia. And I usually thought of inertia as a 2D thing, but it can be any dimensions. So you might have a 3D problem with inertia. Just remember, the trick is, think about what is the distance. And you're going to integrate distance squared. And the nice thing is it's on the formula sheet. All right. So in 2 dimensions, we can talk about the inertia with respect to the x-axis, and that's y squared. We can talk about the inertia with respect to the y-axis. So that gives you x squared. Same thing with moments. There's one other thing we can talk about, which is inertia with respect to the origin. Now, if I'm at a point x comma y, what's my distance to the origin? So origin here, at 0, 0. Here, x, y, what is this distance?
X squared plus y squared.
It's the square root of x squared plus y squared. And so when you square it, the square root goes away. So you just end up with x squared plus y squared. Okay, so another problem. This one's from a final. I remember this one because this was before I got good at drawing pictures. I'm so much better at drawing pictures now. So find inertia with respect to the origin. That's what the notation means when you see a 0. For the region, 0 less than or equal to r, less than or equal to theta, less than or equal to pi, and the density is 1. Let's think about this. Well, there's a couple of things. Here, we have 0 to theta. That's for r. Now, r equals 0. That's the origin. That's not too surprising. R equals theta. We've seen this curve before. You start at the origin, and then as you start going around, you start getting farther and farther away. I stop at pi because theta stops at pi. Theta less than or equal to pi. So this is our region. All right. So what do? Well, we go with the formula. So the inertia with respect to the origin is equal to the integral. Oops, I forgot to put down r down here. There we go. Now that's fixed. Integral over our region. All right, distance squared. We'll come back and fill this in. Density and dA. And the formula sheet, this dA is called measure. But basically, I'm just saying, here's the formula sheet. Formula. We're going to do this in polar because it's given to us in polar. And they probably gave it to us in polar for a good reason. So we should trust them. They seem like nice people, the people who write problems. They give us nice treats sometimes. In polar, distance to the origin, what is that? R. Yes. So the distance becomes r squared. The density? 1. And the dA? R dr d theta. Where does theta go from? 0 to pi. Where does r go from? 0 to theta. Okay. Well, r squared times r is r cubed. What's the integral of r cubed?
1/4 r to the 4th.
1/4 r to the 4th. Evaluate from r equals 0 to r equals theta, d theta. This becomes integral 0 to pi of 1/4 theta to the 4th. What's the integral of 1/4 theta to the 4th? 1/20 theta to the 5th, right? You add 1 to the exponent, which becomes 5, and divide by that. Evaluate from theta equals 0 to theta equals pi. Well, when you plug in 0, you get 0. That's good. When you plug in pi, you get 1/20. And then pi to the 5th. And that's the answer. All right, any questions about inertia? I think there's one problem on your practice quiz. So you'll get to practice it. And I think that one's in 3D. Okay. Well, on to today. Quote from Bill Watterson. We're so busy watching out for what's just ahead of us that we don't take time to enjoy where we are. I think this is true. Sometimes we think too much about the future. Enjoy the now. You only get to have this now once. You might as well enjoy it while you can. Because it's pretty good. It's pretty good. I understand college is stressful. I once went to college. And this was back in the day. I mean, I wasn't quite old enough to go there when they were doing, chiseling into stone tablets. But yeah, it's been a while. And I understand it's stressful, but it's also wonderful. So don't miss out on it. Enjoy your time. Now, what are we doing today? Well, we're sort of gearing up for something that's coming up in the next few lectures, but what I like to think of is we've been able to take polar coordinates and in certain situations use polar coordinates to do integrals. And it's been pretty helpful. And that works well for 2D. Let's step it up a notch into the third dimension. So we're going to talk about integration in 3D coordinate systems. Specifically, we'll look at the cylindrical and the spherical. And the important thing is how you chop things up. So there's dv is r dz dr d theta, and dv is rho squared sine phi d rho d phi d theta. And you might say, how are we supposed to remember these things? Well, it's on the formula sheet. That's one way. But in some sense, the cylindrical is not too surprising, because what's cylindrical? It's a polar plus z. And you said in polar I had an r, so that makes sense. So I'll remember that one. And at the end of today, I'll show you how to remember spherical. So much so that you'll remember it years from now, decades from now. Even after you've forgotten the names of your children, you'll still remember this formula. So that's how good it is. All right. So, let's recall. There are three aspects of integrals. This is something I've said before. It's something I'm going to say again. And once you understand that, you can set up any integral to work out. You have to describe the region. And different coordinate systems are just different ways to describe things. Different ways to describe location, different ways to describe surfaces. So, okay, describe your region. You have to be able to express your function. So maybe if you're in Cartesian, you have x, y, z. Maybe if you're in polar, you've got r theta z. Sorry, cylindrical, r theta z. And if you're in spherical, you got your theta, phi, and rho. But you just switch. That's not so bad. It's the third thing that we need to talk a little bit about. How do we break things into small pieces? So in other words, we're going to sort of chop up our space into tiny parts and say, how do we measure that piece in terms of our variables that we have? So we'll start with cylindrical coordinates. Just remember it's polar plus z. So you have some basic formulas for polar. And of course you have z equals z. I will mention, of course, I should have pointed it out before, but in your formula sheet, when in doubt, it has lots of good stuff. This will help you as well. There's your various formulas to get back and forth between polar and Cartesian and polar and cylindrical and spherical. Now, what is cylindrical good for? Cylindrical is wonderful for any time you have rotational symmetry around the z-axis. So if you've got something that spins around the z-axis and the shape is maintained, perfect for cylindrical. It's what it was made for. Now, how do you know? If you have something that you describe and there's no theta terms, that means that you've got that rotational symmetry. And for that, I recommend you work in the RZ plane. And the RZ plane is just another fancy way of saying, take your three-dimensional space and just take a half plane coming off of your z-axis. So this is the RZ plane. And it doesn't matter which half plane you take, because rotationally symmetric means any half plane will work. All right. So, what's going on? Well, if I want to understand how to break up volume, I've already written down the formula. It's r dz dr d theta. We can think of it in saying, well, you've got your r, theta, and z. You want to perturb them all and say, what is being formed? So you perturb r a little bit. So you go out a distance r, perturb r a little bit. You move some angle theta, perturb theta a little bit. You move up z and perturb z a little bit. And you form this shape. Now, it's not quite a box. The box is sort of slightly bent in some sense. You have these sort of circular pieces here. How do you find the volume? Well, you think about, well, I know how to find the area down here. That's the polar. dA is r dr d theta. Now I just add the height. So that's where you get the dz from. So the dz is height. Base times height gets you volume. And that's basically all you have to remember. Once you do this, the rest of it's just a matter of setting it up. Make one note here before we leave. dz dr d theta, I will say this is probably a default ordering. It's not the only ordering, but when in doubt, this is a good one to go with. But you have options. Okay. We have to make sure we move at a pace here. Any questions before we go to an example? Cool. Find the center of mass for a solid with constant density given by the square root of x squared plus y squared is less than or equal to z is less than or equal to 2. Okay. Couple of things we should figure out. It says constant density, but it doesn't tell us the constant. Which constant should we use?
1.
Yes. So the moral is, if it tells you constant density, you can pick the constant, except you can't pick 0. And so pick a convenient constant. So we'll choose delta equals 1. The thing here is, regardless of what constant you pick, when we go for center of mass, there's a ratio. And so those constants cancel out. So if it says constant density, think 1. Now let's think about the shape. Because it is not 2D, it's 3D. Spoiler alert, it says solid. That's a big clue. Do we recognize some of these things? Oh, we see an r. R less than or equal to z less than or equal to 2. Okay. Does that help you recognize the shapes yet? Let's work in the RZ plane for a second. RZ plane. So we're told r less than or equal to z. So what should I sketch here? Well, start by saying r equals z. And we want r to be less than or equal to z, which means we're going up above this. What else do we know? Z less than or equal to 2. So we're going down from here. Say, okay, so what does that give us? Well, it gives us this triangle. Cool. Now that's in the RZ plane. But what's going to happen? We're going to spin it. And when you spin that triangle, what shape do you form? Cone. So we now know our shape. It's a cone. And we can even say some things. The radius of the cone is 2. The height of our cone is 2. So, we have to find center of mass. Can we make it a little bit simpler on ourselves in any way? Actually, there's a couple of ways we can make it simpler. But one way would be helpful. Do you notice anything about the cone? Symmetrical. Symmetrical where? It's symmetrical around z. So shape is symmetrical around z-axis. Now that's because it's a beautiful shape, but it's also constant density. So shape plus density about the z-axis. Now, what does that tell us? It tells us that the center of mass has to be on the z-axis. So that implies center of mass is on the z-axis. But what does that tell us? Well, how am I on the z-axis? What kind of points look like they're on the z-axis? 0, 0, and z bar. So we're 2/3 the way done. Isn't that great? We haven't even done an integral yet. Nice. Okay. We're doing awesome. Okay, what's next? Well, we got to find z bar. So what's the formula say z bar is? Give you a moment to think about it. It's a ratio. It's m xy over m. One of these we can do without an integral. M. What is m? Well, let's think about it. According to our formula, it's the integral over the solid of density dv. But what have we picked for our density? 1. So it's the integral of our solid of 1. What does that give us? Volume. Now, do we know the volume for a cone? It's on the formula sheet. What? They want us to know stuff? No, they want you to look it up. You don't have to memorize it, just have to know where to find it. Okay, so the volume of a cone. So the volume of a cone is 1/3 pi r squared h. What are r and h? 2. Radius is 2, height is 2. So this makes it 8/3 pi. So that's great. We've already got 8/3 pi downstairs. So that means we only have to do one integral for this problem. That's our favorite number of integrals. Well, maybe 0. But, so this is our second favorite number of integrals. Is 1. All right, so let's take the moment. Integrate distance, density, and dv. So, what is the distance? Because we've got to go with the distance here. Distance to the xy plane. Z. The other thing is, you're computing z bar. So it's got to tell you something about z. So if you're computing z bar, that has to match what you're computing. So it's z. And density is still 1 dv. And we're going to do this in cylindrical coordinates. So we say cool, integral, z, dv, we've already mentioned, this is r dz dr d theta. So we have an r dz dr d theta. Let's go through and set this up. Where does theta go from? We have to describe our region. 0 to 2 pi. All the way around. It's a full circle. So when you got that rotational symmetry all the way around, 0 to 2 pi, full circle. All right, now, everything else come to the RZ plane. What can we say about R? Where does R go from?
0 to 2.
0 to 2. Where does Z go from? So pick a value for R. You're going between two curves. What are your two curves? Yeah, R equals Z, or Z equals R, and Z equals 2. So just a reminder, This comes from use the RZ plane. Now we just have to carry this out. Okay, well, not exciting, but we go ahead and do the work. 0 to 2 pi, 0 to 2. The integral of z times r with respect to z.
Z squared over 2.
Z squared over 2, and don't forget the r, it comes along for the ride. So I'll put that in front. 1/2 r z squared. Evaluate from z equals r to z equals 2, dr d theta, which becomes integral 0 to 2 pi. We're cleaning up. Now we got to plug it in. When you plug in 2, 2 squared is 4 times 1/2 r makes it 2r. When you plug in r, r squared is r squared times 1/2 r is 1/2 r cubed, and we subtract. Okay, well now we integrate these pieces. What's the integral of 2r minus 1/2 r cubed with respect to r?
R squared
R squared
minus 1/8 r to the 4th.
minus 1/8 r to the 4th. And I'm thinking, oh my gosh, are we going to have to deal with fractions? Let's find out. Good news, when you plug in 0, you get 0. Woohoo! Still check. When you plug in 2, what do we get? 2 squared, 4. 2 to the 4th, 16. Times 1/8, 2. So you get 4 minus 2, which is 2. So this is the integral of 2. Well, that's 2 theta from 0 to 2 pi, giving us 4 pi. Is this z bar? No. But we're close. What do we need to do? Put it up here, right? Okay, so we're almost there. We say, okay, this is the same as 4 pi. Then we'll just flip this upside down. Times 3 over 8 pi. The pi's cancel. 4 goes into 8, leaving us with 2, giving us 3/2. So our final answer is 0, 0, 3/2. Is this a reasonable answer? Think about where is 3/2 in relationship to this cone. Now, if it was outside the cone, is that a reasonable answer? Yes. No. Good. Some people were saying yes. No. The center of mass has to be somehow, you can't be outside the mass and be its center. But it says we're biased towards the top. Does that make sense? So 3/2 is like 3/4 the way up. Should you be closer to the top than the bottom? Yes. Why? There's more stuff on the top. And so you expect it to be biased towards the top. So that's good. Oh, good. I hate to say it, but this was also an exam problem. Yay. Not that I hate to say it, but this one takes more work. It's like everything we show you could be on the exam.
Are we going to have to do it for x and y and z or some equations?
No, we would never do that. No, we never would do that.
As long as it's not your problem. Don't make it number 10, please.
Well, I never know what I get to write. I'm always the last one. So just think about what would no one like to write a question about? That's what Steve will write a question about. All right. Spherical coordinates. So spherical coordinates, as a reminder, you have theta and phi. Theta acts the same as before. So theta is this same thing downstairs. So theta is measuring off the positive x-axis. This right here is your change in theta. A little bit of perturbation in theta. What does phi measure? Do you remember? It's angle off the positive z-axis. So straight up, that's phi equals 0. This little piece here, that's your perturbation. That's your change in phi. Where does phi equal pi point? Phi equals pi is straight down. Where's the xy plane? Phi equals pi halves is the xy plane. All right. So you start at 0. By the time you hit pi halves, you're 90 degrees off the z-axis. And what's 90 degrees off the z-axis? It's the xy plane. So phi and theta give you your direction. Then what do you need to do? Go a distance. So rho is how far out you go. So rho is the distance. And so here you see a little perturbation of rho. So you have the same things as before. These are from the formula sheet. I'm not going to go through them. Spherical can be a little bit cumbersome at times, but it's really good at some very particular things. It's like, I don't know if you've seen, there's a movie that came out a while back called Taken. And there's Liam Neeson as the actor. And he's on the phone talking to the kidnappers. And he tells them, I have a very particular set of skills. That's spherical coordinates. It can't do much, but it has a very particular set of skills. And when it's the right setup, it's amazing. So what are you looking for? Spheres and cones. Almost all other shapes can be challenging, but when you've got spheres and cones, it's amazing what spherical coordinates can do. And it turns out a lot of things look like spheres. For example, planets look like spheres. So you can do all sorts of fun analysis. All right, now what you see here, that little shape, and it's hard to make it out. That's why the handout has a better printout. That's the shape that you get with your little perturbation. And I claim, without proving it today, we'll talk about why it's true later this week, that dv is rho squared sine phi d rho d phi d theta. Now, why does this make sense? Even if I'm not going to justify it. Let's talk about a couple of things. This is supposed to be a volume. If I'm trying to measure a volume, how many times should I have a distance showing up in the formula? 3 times. D rho is a distance. What about d phi and d theta? Those are not distances, they're angles. So these aren't distances. So we're still 2 distances short of 3 distances. That's why you need that rho squared to get you up to 3 distances. Now you might say, okay, but why the sine phi? Well, if phi is very small, I'm up here, this little piece here. Whereas if phi is, say, close to pi halves, I'm down here. And you can see that I might change my size pretty dramatically, say from phi equals 0 to phi equals pi halves, because I go from a little tiny thing to a fairly substantial thing. So sine of phi makes sense to be there. It also makes sense there's no theta term, because there's change theta, the whole picture spins. But it still is, why is it exactly that? We'll talk about that later in the week. But we still have a few minutes left, and I promised you I was going to give you a way to remember this formula. Because it used to be the case that we wouldn't give people a formula sheet. I know, the Dark Ages. And they had to remember these things. But it turns out that this one is surprisingly easy to remember. So, there's a song. I'm going to sing it to demonstrate. Then we'll sing it together. Now, you might say, but what if I don't know the song? Well, you will recognize it. It's based off of the song, Row, Row, Row Your Boat. And here's how it goes. Row, row, sine of phi, d rho, d phi, d theta. Now, you might say, wait, how does that help me? Well, you've got a row, row. So there's 2 of them. That's a row squared. Sine of phi. d rho, d phi, d theta. Yes? That's the formula. Okay, so I sang it once. We now need to do it together. You ready? Rho, rho, sine of phi, d rho, d phi, d theta. Now, there is, of course, the rest of the song. Merrily, 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 calculus is a dream. So, we'll pick up again next time. That's it for today.